Hi everyone, I'm Jose, and today we'll be talking about Wigner molecularization in asymmetric quantum dots. First of all, this is a talk about Coulomb interactions in quantum dots, and what I want to show you in this talk is that if you have a quantum dot and you fill it with multiple particles, unless this dot is very small and very isotropic, um, the way of thinking about these multiple particle states is not the one that we used to do with a single particle picture in mind. I will show you that in reality, these multi-particle states tend to form what are called Wigner molecules, and this has some consequences. For instance, the singlet-triplet splitting decreases quite fast with the dot length in these Wigner molecules, and the anisotropy only makes it faster. I will show you that silicon dots are much more affected than gallium arsenide and germanium dots, and this has some consequences on quantum computation. This complicates polyspin blockade readout and limits the exchange coupling. But before getting into details, I wanted to give first a very brief introduction. And well, as you're probably seeing in some of these talks, in this field, there are already very nice single qubit gate fidelities, are already beyond 99% for both electron and hole qubits have been demonstrated. And we are starting to see very nice results also in 2-qubit gates. And there's even a 4-qubit processor with whole qubits in germanium. So I would say that this field is growing quite fast, but if we want to go even further, we actually need more qubits, so we actually need more and we want more. So to go beyond, we need to understand the many details that affect our qubits. One of them, which is the focus of this talk, is the Coulomb interaction, or more general multi-particle states. So why do they matter? And there are already some theoretical works that show that if you have multiple electron states encoding a qubit, since you have multiple particles, you may be able to screen part of the charge noise fluctuations that come from the environment. So that's a good thing. You could improve potentially the coherence times of your qubit. There's already this paper in which it seems that there could be a slightly enhanced dipolar coupling in the end. If you put more electrons, the wave function tends to swell, so you may have a larger wave function, which in turn gives you a larger dipolar coupling for faster interactions. And it has already been shown experimentally that if you have multiple particle states, you may be able to find multiple levels that can be manipulated coherently to form a qubit. Our goal in this talk is going to be to understand the Coulomb effects in quantum dots and its consequences on semiconductor qubits. So we will focus on the two-particle problem, both for electrons and holes, and we'll make use of a very, very simple model, which is called the Hooke's atom problem, which is basically Coulomb repulsion plus the harmonic confinement of the dots. And we will do this in the 2D and single band approximation, which basically means that we won't focus on Valley physics or heavy hole, light hole interactions for holes. And this is a very general model that can be applied to very different materials, as I will show you. So here we have this very simple model, which is called the Hooke's atom problem. And you have basically two particles in a harmonic confinement with the Coulomb repulsion. As a general rule, we will take X as the weakest confinement direction. And the relevant characteristic length of our problem is going to be this harmonic confinement length along the weakest direction, which we call Lx. And if we go to the center of mass coordinates, we can actually separate our Hamiltonian in two terms. One for the center of mass, which is basically the harmonic oscillator problem, which we all know how to solve. And we have another problem, which we will need to solve numerically for the separation of the coordinates. And so this is the problem we need to solve. And before that, it's useful to define a few quantities. So here you have the characteristic energy scales of our problem. First of all, we have the orbital confinement. As associated to the harmonic confinement. And we also have the Coulomb repulsion at the characteristic length of our problem. So, with this, we can actually define a couple of adimensional parameters, which are called the Wigner ratio. And this is basically the ratio between your electron-electron repulsion over the orbital splitting. This basically tells you how strong your electron-electron interactions are. So, the larger this lambda W, the larger your dot, the larger your Coulomb interactions. The smaller it means the smaller the dot, and the smaller the Coulomb interactions. And we also have the anisotropy associated to alpha, which is basically, if alpha is equal to 1, we are in the isotropic case. If alpha is greater than 1, we are in the anisotropic case, and if it tends to infinity, we go to the 1D limit. So we can take a step further and redefine our coordinates in terms of adimensional parameters in a way that we reduce our problem to this adimensional Hamiltonian, which we can solve numerically in terms of the strength of the interaction, this Wigner ratio, and the anisotropy. So we solve our Schrodinger equation in finite element solver. And the first thing we notice is this spectral compression that can be summarized in this slide. So first of all, let's take a look at the non-interacting case. There are no Coulomb interactions. Then if you have two electrons and you put them in your quantum dot and they have opposite spins, they will tend to go to the harmonic ground state, to the s orbitals, let's say, and form a singlet state. If you have same spin, one of the electrons will actually tend to go to a higher orbital, right? So you will have a p-type two-particle wave function in the triplet state, and your singlet triplet splitting is basically your harmonic splitting. Now, let's say we go back to reality and we have Coulomb interactions. So even if your two electrons have opposite spins, they will actually try to avoid each other. And this can already be seen in the density wave functions here of the singlet state. So there's already in this density wave function, you can actually see a node when the two particles tend to be at the same distance. And there's actually, these two particles tend to dance around one another, avoiding each other, okay? Moreover, in general, both the singlet and triplet, if you compare with the non-interacting case, the wave functions the density wave function will tend to swell, basically because the electrons again are trying to avoid each other. One consequence here is that you see here this spectral compression, and your singlet triplet splitting is going to tend to be smaller than the confinement splitting. Now we can go a step further and go to the anisotropic case. And in the anisotropic case, there's a weaker confinement direction. Since the two electrons are trying to avoid each other, they will actually try, instead of doing this kind of dance one around the other, they will tend to split apart along this weaker direction, forming what are the so-called Wigner molecules. So here you have your singlet state, which looks very similar to a p-type orbital, and you have also your triplet states. And in here, the singlet triplet splitting is even smaller, and you can actually guess that from the shape of the wave functions. You have here that the density wave function of the singlet state and the triplet state is very, very similar. So let's now take a closer look at the singlet triplet splitting reduction. And you have here a plot of the singlet triplet splitting in units of the confinement energy as a function of the inverse of the anisotropy and the Wigner ratio. And when the inverse of the anisotropy is 1, you basically are in the very isotropic case. When you're at 0, you're in the 1D limit. Everything in between is basically an isotropic dot. And the Wigner ratio, when it is 0, it means that your orbital energy is dominating your electron-electron repulsion. So it basically means you have a very, very small dot. And as you increase this value, it basically means that your electron-electron interactions start to dominate. And this basically means that you have a larger and larger dot. And well, what we find is that the single triplet splitting actually decays quite fast, exponentially indeed, as a function of the Wigner ratio. Moreover, the more anisotropic your dot is, the stronger, the faster the exponent in the exponential decay. So the stronger the effect. And well, so far we were talking about dimensional quantities, but let's put some numbers and see how this translates into silicon, gallium arsenide, and germanium dots. So you know this Wigner ratio, we can find that it's proportional to the effective mass and of your electrons or holes, and inversely proportional to the permittivity, and it's linearly proportional to the length of your dot along the weaker direction. So what we find is that you can translate, let's say, we take a quantum dot with length of 15 nanometers, and we can translate this into a Wigner ratio for silicon, gallium arsenide, and germanium. And due to the differences in effective masses and permittivities, we find that silicon is actually the most effective. So you know, a 15 nanometer long silicon quantum dot is already around 5 in the Wigner ratio. So it's already around here, which means already a very dramatic reduction in the single triplet splitting. Gallium arsenide and germanium, on the other hand, are much less effective. And well, so far we have taken a look at the very simple model, but how does it translate to more realistic devices? And to answer that, we actually perform simulations with more realistic nanowire dots and perfectly isotropic two-dimensional dots. And you know, we focused on holes basically, and this was because in the end, with electrons, this becomes, due to the Wally degree of freedom, this becomes a very disorder-dependent problem. So, which goes beyond the scope of this work. But if you are interested about valleys and Coulomb interactions, you can take a look at this paper here. So we solve the single hole wave functions and eigenenergies with k dot b, and we extend our calculation to a two-particle states using full configuration interaction. I won't get into details, but what I will say is that the very simple model agrees with more realistic simulations. And you have here a comparison with of the Hooke's problem, with the k dot b problem of the singlet triplet splitting in units of the single particle orbital excitation. And it agrees pretty well. Now that we understand the Coulomb interactions in quantum dots, so it's the moment of taking a look at the consequences for quantum computation. And we first focus on the Pauli spin blockade readout. So you know, in this readout mechanism, you go in the tuning near the 1102 anti-crossing, and if you are in a singlet state, single 1-1 state, as you go to the anti-crossing, you know, there's a moment in which you basically have a transition towards the SO2 state, and this leaves a charge signature that you can detect, and you use that to say the qubit is in the singlet state. Now, if you are in the triplet state, you start here, and as you go to the anti-crossing, in principle, you don't expect any charge transition. So you can distinguish your singlet from your triplet state. Now, what happens if you have a very, very low triplet state? This will be very similar to what happens when you have very low valley state in electrons, but this can apply also to holes. So what happens here is that, you know, this low energy triplet may induce this anti-crossing here, which basically allows you to find a charge signature even if you have a triplet state. So you may be assuming that your charge signature is basically a signature of a singlet state, while in reality is what you have is a triplet state. So we quantify this And to do so, we basically find that there is an optimal readout point in the tuning. We go to this optimal readout point and we calculate this optimal probability of finding a charge signature when you are in the singlet state, and not finding, well, minus the probability of finding a charge signature if you're in a triplet state. And we want to maximize this quantity. So what we find is that if you have very low values of the singlet triplet splitting in terms compared to the tunnel couplings, you basically have very reduced values of this probability. And another important effect for quantum computation is the exchange interaction, which is also affected by these states. So the main definition of the exchange coupling is just there is the energy difference between the triplet state and the singlet state. And the singlet state is bent with respect to the triplet state, but by the presence of excited singlets, right? That is not supposed to happen to the triplet state. But if it happens also to the triplet state, then the relative bending of the levels is going to get reduced, let's say. So your expected exchange coupling is going to be limited by the presence of a low-lying triplet state. And you have here the formula for the real exchange coupling in terms of the exchange coupling for triplet state at infinity. So this can get reduced by a factor of 2 or 4 quite easily. Another relevant question related to the exchange coupling is what happens at the symmetric operating point. So this working point is far away from the charge anti-crossings, so you may expect that the low-lying triplets are not very important. And we have here a plot of the energy of the singlet and triplet states as a function of the tuning, centered at the symmetric operating point. This is an important working point basically because here the qubits are insensitive to charge noise, so it's a very promising working point for 2-qubit gates with exchange coupling. And when your triplet state, your excited triplet states are supposed to be at infinity, this triplet state is supposed to have no bending, be at 0. So the exchange is pretty large. But in reality, if you have a low-lying triplet, you have this bending that you can see here clearly. And even if you have a 1 milli-electron volt low-lying triplet state, it already affects a lot your exchange interaction. You can reduce it by a large factor of 5, factor of 10 even, if you have an even smaller single triplet splitting. So this can be very important even at the symmetric operating point. So just to finish, we go back to our take-home messages, and I hope I have shown you that thinking in terms of the single particle picture is incorrect. The singlet triplet splitting is strongly affected by the length of the dot in multi-particle states. Silicon dots are more affected, and this can complicate readout and the exchange. And the way to go is basically to aim for smaller and isotropic dots. With that, I will thank you for your attention.